The other conferences that I've attended, I would say that they've been pretty straightforward, where you attend the talk and then it's kind of over, you take a break, and then you go to the next talk. What's really unique about CppCon is the fact that after the talk is done, it's welcome and encouraged to engage in dialogue with both the presenters and other attendees.
All right. Hello, everyone. I'm Hamish. I'm a software engineer at Bloomberg, and I'll be presenting on building a high-performance binary serialization format within place modification. So just to start off, I'd like to give a definition of serialization. So I'm saying that if you have a data structure and you want to, say, send it over a network or persist it to a file or to share it between processes, essentially, you're going to need to turn it into a sequence of bytes. And then on the other side, you're going to have to turn those bytes back into the original data structure again. So an example of a data structure is this one. It's a trade because I'm in finance, so kind of makes sense. So how do I serialize this? Okay, has anyone got any problems with this? Anyone can see anything that could go wrong with this? Yeah, Chris.
Padding bytes?
Yep, we've got padding bytes. Let's go back to the original type. It was this. So anything else?
We don't know the alignment of the destination.
Yeah, exactly. Alignment could be wrong as well. I guess that ties into padding bytes as well. Yeah. Sure, exactly. Yeah, it's even more deep kind of problem with this. Yeah, perfect. So, like, just for the most kind of simple problems with this, I've said the endianness is a problem. So, on different platforms, these types could be in different byte orders. So either like big endian or little endian, and then the size of types is a problem as well. So on different platforms, a long could be a different size, for example. And then at the end there, you can have some padding bytes in between your strings and your last unsigned flags there. That'll typically be 2 padding bytes, but it could be different on different platforms. So here I've got a better version of this code. So I'm taking each member one by one. I'm swapping it to network order, and then I'm just writing it into this buffer. And then each time I increment by the size of that type. So it's better, but it's still not great. So I have a lot of boilerplate here. I have to have my sending and receiving code have to agree exactly on the format. And evolving the schema is not possible. So, and it's also not easy to see how to encode like more complex kind of nested documents like maps and arrays and that kind of thing. So how do we improve on this? So 2 broad-based approaches we can use are schema-based approaches and schemaless approaches. So in a schema-based format, the receiver has to know something about the shape of the data in order to make sense of it. It has to sort of see some information about how it's encoded. And then in schemaless, senders and receivers can share data without having to know anything about its format. So in your typical schema-based format, we define a type. It's usually in some kind of a DSL. So here's an example of my trade struct as a protobufs message. So often you use these DSLs in order to generate code as well. So you'll generate classes that can access these in C++, Java, Python, or whatever language you're using. And the sender and the receiver need to agree on the schema to an extent, but they don't have to agree 100%. So I'm still allowed to evolve this in some ways. I can add a field, for example, and that won't break existing receivers. On the wire, it typically looks like a sequence of tag and value pairs. So the tag consists of the field number. So that's the number that's given on the right in the DSL after the equals. And then the actual value itself, so you can see here, it gets turned into a sort of a sequence of these pairs. And then almost every field is encoded as this var int type, which means a variable length integer. So, yeah, as you can see, this this format is somewhat self-describing. I can traverse through it without knowing the exact schema. If I want to make sense of it, I need to know a bit more information about it, though. If I only saw the fields on the right here, I wouldn't know what the field names were and what the original types of the original message were. So what if I don't know the shape of my data up front? So, I just want to encode anything, and I potentially want to encode arbitrarily complex documents as well. So if I want to have maps nested in arrays, nested in maps, and so on and so forth. If I need that, I'll need to move to a schemaless format. So in schemaless formats, you can encode anything at all, pretty much. You usually get some kind of a dictionary style API. You can set fields, you can get fields, and so on and so on. Examples of schemaless formats include JSON, BSON, MessagePack, CBOR, flatbuffers, and there's a ton of them actually. And what these have in common is they usually encode the data as a sequence of tag and value pairs. Not always, but it's quite a common encoding. So here's an example of a document encoded in both JSON and in MessagePack. So on the left-hand side, you have JSON. On the right, you have MessagePack. As you can see on the right, you've got these tags in green and the values in blue. So this tag 84 means I have a map of 4 elements. And this tag 85 means I have a string of length 5, and it's followed by the string price. And then there's the value 100. And then here, I have a string of length 6. It has the value volume. And then tags CD means it's a uint 16. And that's my value 5,000 after that. So as you can see, these tag formats are pretty creative about encoding a lot of information in a small space. So in the previous example, you can see that my integer 100 actually doesn't have a tag on it. And that's because if my integers are less than 128, I actually just store them as themselves. And then all other tags must have the high bit set. So it's possible to know if it's a tag or if it's an integer that's less than 128. And they also encode true and false as a single tag and so on. So yeah, a question I want to ask is what's the cost of using a schemaless format? If I have a message and I want to be able to read it and operate it and change it in some way, I usually need to decode it into an in-memory data structure first, and then make my changes and then re-serialize it into the packed form. So what if I want to avoid this? If I'm doing a lot of these operations every second, I might want for example, to pull a document out of a database and make some small and targeted changes to it, and then write it back into the database. Or let's say I'm receiving messages on a stream or something, and I want to just pull a single field out of each one of them. In this case, I might want to be able to do this much more quickly without having to re-serialize my document every time. So I thought it'd be kind of interesting to try and build a schemaless serialization format where you can change its contents in place without having to re-serialize it. So yeah, in the rest of the talk, I'm gonna show you how I tried this. So the first thing I wanted to try was to build a baseline. So a very simple kind of format which just stores everything as a sequence of tag value pairs and makes its modifications in the simplest way possible. And the purpose of this was to build a sort of like a baseline to benchmark against, really. So to have a point of comparison and then something to optimize and improve. So for my baseline serialization format, I created one that supports strings, ints, floats, maps, and arrays. It's encoded as a sequence of tag value pairs. The tag encodes the type and the size if necessary. The values are in little endian to be friendly to modern CPUs. Our maps are encoded as a sequence of key value pairs. And then our arrays are just encoded as a sequence of values. So it's pretty simple. And our interface is going to look a bit like this. So it's pretty similar to what I showed previously. You have a bunch of accessors at the top to access the current field as various types. Then you have a bunch of, I guess like mutators. So you can turn the current value into an array or turn it into a map. You can assign a value to it, so some kind of primitive type. You can also append to an array. You can set a key in a map. And then at the bottom are the accessors if your value is a map or an array. So you can pull out a key and value if you know the key. And then if you're an array, you can pull out a value at a certain index. So to implement the common operations, in order to implement read, I just implemented it in the most simple way possible. So here I have a document on the left, and I'm going to do the code on the right to it. So I create a value, I try and get the timestamp out of it, and then I return it as an integer. So the code is just going to iterate through all these fields one by one until it finds a matching key. It's going to find timestamp, and it's going to return it as an integer to the user. It's just a simple linear scan through the tags and values. And then to make modifications, we're just going to modify everything in place. So in the code on the right, I find price, and then I turn it into a map, and I set its mantissa and exponent to be these values. So I loop through my container, I find price, I replace its value with a map, and then I start to insert these new keys and values into that map. So I insert mantissa, I insert exponent, and then everything else has to move down each time. So it's quite expensive to make a modification. Everything else in the buffer has to move. So how does this perform? I created a simple benchmark, and I parameterized on a bunch of stuff. So I parameterized it on the number of fields in the document, the number of operations we perform in a row, and the percentage of operations that are of different types. So like how many reads, how many writes, and how many of what I call structural modifications. And structural modifications are simply either adding a new key to a map or removing one. And then writes are just changes to existing values, basically. So just a bit of information on the benchmarking step. I used this machine described here, GCC 13, O2, March Native, and so on. I used a machine on which I didn't have too much load. And then one thing I want to say is that all these benchmarks are, of course, micro benchmarks, so they're subject to all the problems where, in production it may work completely differently, and I've not tried this in production at all yet. So, yeah. So here are the results from my baseline. You can see that we do about 1 million reads a second on very small documents, and then we get progressively worse and worse and worse as you add more fields and as you do more writes. So I've got a log scale as well. So the most number of fields is a good maybe 2 orders of magnitude slower than the small number of fields. So it scales extremely poorly. And that's kind of what we hoped for. It was like, it's like a baseline. It gives us lots of room to improve. So the first question I asked myself, one thing I wanted to do as well was to compare it to how much it would cost to simply keep all of my data in a map and then periodically re-serialize it. So on the green is a benchmark in which I serialized after every operation, and then red has after every 4 operations, and on blue it's after every 16. As you can see, it's slightly faster than serializing after every operation, and then it's about half as fast as serializing every 4. Again, it's a log scale. And then it's about maybe a fifth as fast as serializing every 16 operations. So yeah, if your requirements let you say make a bunch of modifications and then only re-serialize after a whole bunch of operations, it would still be faster to just keep everything in some memory data structure and just re-serialize it. So yeah. So the next question I asked myself was, how do I make the searches faster? So on profiling, I found that it spent a ton of its time just looking at what's the size of these various elements in the container. So about 60–70% of the runtime, or at least of the CPU cycles, is going on that. So a lot of time in the searches is basically spent skipping over elements. So if I'm searching for a certain key, I essentially just need to keep on skipping over elements until I find it. And that means I have to keep on checking for every element. How big is it, basically? So one idea I had is kind of put my keys into sorted order. So I take these 2 keys, and I swap them around. And now if you ask the question, can I do binary search, you'll find the answer is still no, unfortunately, because my keys and values are variable size here. So my keys and values are not a regular size. It's very hard to jump to a certain element. As part of a binary search, I need to jump into the middle. So an idea that I had to solve this was to store a table of offsets at the start of the map. So essentially, I take my map, and at the top, I put a sequence of offsets of which order the elements are supposed to appear in. So in this case, I'm basically saying that the key at offset number 6 comes first, and that's the key AA. And then the key B comes next, and then the key C comes last. This means I don't need to store my actual elements in sorted order. I just need my offsets to essentially put them in sorted order. So after making this change, we perform a lot better on the searches. I would have liked to compare this to the previous one. I created a more kind of a more specific benchmark just for this, and it wasn't. It was doing less work than the previous benchmark, so it was a bit of an unfair comparison. But you can see here we're doing a lot more operations a second on the smaller arrays. It still scales pretty poorly. As you go down to larger arrays, you're doing a lot less still. So yeah, an idea that I had after that was, what if I put a list of hashes of my keys at the start of this map as well? So essentially like this. So if I put an array of hashes of my keys at the start of the map, I have a smaller array to search. It's just an array of uints 16t. It's quite easy just to loop over this and find my hash, and then I know which offset it's at. Of course, I could have hash collisions, and I might need to check multiple offsets, but it's a good bit faster. So if I add hashes, I get about a 20% improvements on the smaller containers, and then on the large containers, I actually get quite a big improvement. So I'm almost doubling the speed there. So I asked myself, can I do even faster than that? So in perf, I profiled the search routine, and I found that it's spending a lot of time on this instruction in the middle of the lower bound. So in lower bound, you got a check in the middle to see if you should go to the upper half of the array or to the lower half of the array. And it seems that in this check, it's spending a lot of time. So my guess is that even though it's attributed all this cost to the instruction sub, it's probably attributable to the branch that's just above it. So if you think about it, it's almost impossible to predict this branch just because every time I want to narrow down my array to a half of the array, it's pretty much unpredictable which way I would go. If I could predict it, I wouldn't need to search in the first place. So the mispredicted branch is this one here. An idea that we can use to work around this is to use a conditional move instruction, which people sometimes call branchless programming. So I had the idea of using branchless binary search here. And the idea of this is that you essentially, if you keep the contents of your if statements down to a single assignment, the compiler is much more likely to replace what you've done with just a conditional move instruction. So instead of having a branch in the middle of your loop, you now just have a conditional move. And this conditional move essentially, it's not going to it's not going to be predicted either like one way or the other. It's now like a data dependency instead. In this article, I actually took this implementation from this article. In the article, they actually take this sort of like predicate of like base half is less than key, and then they multiply it by half, and then they increment base by that. And I think that was a kind of like an older trick to make the compiler emit a cmove instruction. It seems it's not necessary on more recent compilers, and I was able to just have an if statement here, and it works just the same. So after making this change, in the assembly, I now have this nice cmove instruction, and then most of the cost is going on the comparison instead. Yeah, and as a side note, I also went down a bit of a rabbit hole on searching. I found this great blog article as well, which I'd really recommend. It has a number of implementations of different kinds of searches. So this one, vectorized counting linear search, is basically that you have a loop in which you run through the entire array and you count how many elements are smaller than your one. And then at the end, your result is your index of your position. It's nice and elegant, and it doesn't have any branches in the middle, so it's completely branchless. At the cost of having to run through the entire array, so it depends on how big your array is. If it's tiny, it's really good. And then just a vectorized standard linear search, which just loops through a lot of elements at a time, and once it finds the element it's looking for, it just breaks out. So yeah, it's a great article. I'd recommend that one. So a comparison of all the search algorithms I tried is here. So counting AVX, which was the counting search, is actually great if you have small arrays. As you can see, it gets slower and slower if you have more elements. And then in red is my branchless binary search. It's pretty consistent even at the really large array sizes, which makes me prefer that one. So I went with branchless here. And after that, I'm pretty happy with the search performance. So I moved on to the question of how do I make modifications faster. So in our baseline format, we perform modifications by just moving everything around in the buffer. And now we've introduced offsets. It's a bit problematic. Can anyone see why that is? Yeah.
You need to update them.
Yeah, exactly. Yeah, but each time I update anything in my map, I now need to run through my offsets and update all of them. So if I were to take this int value, which is the value of key B, and turn it into a double, I'm going to increase its size in the process, and the two elements afterwards are going to change position, and then I'm going to have to go into my offset array and change the positions of these offsets. So the 6 and 13 are going to need to change into a 10 and a 17. And you might think that's not a big deal, right? I can just run through this offset array and conditionally update ones that are greater than the offset of the element I've changed. And it's true, but the real problem comes if the map is nested inside other maps. So to understand why it's a problem, I've created this. So it's sort of 3 maps nested inside each other. So like here we have A, and that has another map inside it that has key B, and that has another map inside it. I've kind of color-coded them so the document on the left has the same colors as the encoding on the right. In this case, if I was to go and update the int at the key C and turn it into a double, I've now changed the offset of D. And the problem is D is stored in a map that's actually a few parents above my current map. So now if I have a large amount of nesting, I have to somehow do some kind of walk up all my maps and update all offsets as I go. And that will need me to either store parent pointers in my maps to be able to track through and locate my parents, or I would need to track through what path I've taken through my document in order to find my current element. And if I had parent pointers, I'm going to have to solve exactly the same problem for my parent pointers as well. So I decided not to do that, and instead to move elements out of line if they're containing elements. So the idea here is now my offsets can point anywhere at all in the buffer. So here I have my first map is now pointing to my second map, which happens to be the end of the buffer, and then that's pointing back to the third map that's kind of in the middle. So now, my offsets are now expressing how my nesting works, essentially. And my offsets have basically just become small pointers at this point. So now I have pointers, I need to answer a question of how do I allocate space for all these elements. So a potential idea is to implement a bump allocator. And the idea of a bump allocator is that you keep a pointer to the first bit of free space in your buffer. So here I start out with an empty buffer, and my bump pointer points to the start of it. And I allocate a map, and my free space pointer is now bumped up and points to after that map. And then I allocate a key and value, and now my free space pointer is pointing after that. And now my map is also pointing at its value that's contained within it. And I allocate another key and value. Right, I keep on increasing my bump pointer. Right, if I now want to allocate another key and value and put it in my map, unfortunately, my map has now reached its capacity. So it says 2 out of 2 there. If I want to allocate another map, I'm going to have to allocate another one. So that's going to look like this. And now the free space of my original map is now wasted. So I can now allocate my other value, and I can put it into my map, and I've got a bit of wasted space at the start of my container. So yeah, clearly the strategy wastes a lot of space. Eventually, I'm going to need to compact my entire buffer. I'm just going to run out of space. So how can I improve on this? An idea that I had was to add a free list into my container. So basically, thread a free list through all the free spots in the container, and then preferentially allocate from that first. So a free list allocator is going to look something like this. I'm going to store elements in my map that basically tell you how much free space is at that point. So here my free list starts with a single element, and the free size basically encompasses the entire container. So I've got free size 100. And then each free list entry also has to encode a pointer to its next entry as well. So here it doesn't point to anything, so it just has next is 0. So how this would look if I was going to create a map, I'd create a map and I would carve a bit of space out of my first entry of my free list and then reduce its size. So now its size is 88, and I have a map. So I can add keys, I can add key AA, and I can add key B, and now I just keep on like taking a chunk out of that free spot. And then here, I've got to the point of needing to allocate a larger map. So I carve a bit of space out of my free list, and I leave free size 47. And now what I can do is I can put another free list entry into the space I just freed up. So now I have free size 12 at the start of the container, and now my free list is pointing there, and then that's now pointing to my last free list entry at the end of the container. And then I can allocate my C in there instead. So I can use space a little bit more efficiently. So there's a couple of algorithms you can use if you're implementing an allocator. Actually, there's tons. I've only listed 2 here. But I tried doing first fit, which is where you basically take the first block from your free list that can satisfy your allocation. And then I did, and then I also did best fit, which is where you take the smallest block which can satisfy it, so the best fitting. And then I benchmark both schemes in terms of performance and wasted space. In terms of performance, you can see that the first fit starts off performing pretty well. And then as you do more operations, it starts to perform worse. So it's kind of as you expect. You know, as your buffer just gets more fragmented and you keep on sort of taking chunks out of large blocks and leaving irregular sizes left, you get more and more fragmentation. On the other hand, it seems that best fit is getting faster, which is kind of strange, and I suspect that it might just be because after performing a lot of operations, a lot of the container is in cache. So I don't think it's actually improving in complexity as you do more operations. And then with first fit, though, you can see that the space wastage is absolutely massive. So yeah, after doing 16,000 operations, you're wasting about 40% of your buffer, which is a lot of space. And then if you are using best fit, you're only wasting about 16, which is still maybe quite a lot, but it's not as much. So yeah, I was curious to profile this and to see like where all the time is going. And in the free list like walking algorithm, it essentially spends a lot of time grabbing the free space in the current entry of the free list. So just looking at how much free space is in that entry. And you can see a lot of the time is being spent on that mov, which is the reading of the free space size. An idea that I had then was, what if I can prefetch free list entries as I walk through the free list? So in my free list walking thing, in this one it's the first fit one. Wait, is this first fit? Yeah, it's first fit. So yeah, essentially at the end of the loop and at the start of the loop, I prefetch the entry I'm about to look at. And you might think, like, why would this make anything faster? I'm just about to read it anyway. And I suspect what makes it slightly faster is that it can do this in parallel with checking if the free list offset's not equal to 0. So it can be prefetching that and doing this comparison at the same time. And then if it turns out that the free list offset was equal to 0, I've just done a harmless prefetch of the start of my buffer. And the start of my buffer just has like a header in it of the like free size left and the free list pointer and so on. So after implementing that, I get about a 15% performance boost if I'm using best fit, and I get no improvement at all if I'm using first fit. I guess in first fit, it's likely to find its element pretty quickly, so it doesn't benefit too much from having the elements prefetched. So yeah, after doing this, I got quite excited, and I I started to throw in prefetching around the entire code base. And it didn't make any improvements anywhere. In fact, it just made things a lot worse. So I'd recommend not going wild on prefetching, and really, like, you only want to use it if you are prefetching an address that's very likely to not be predicted by the compilers. So in the free list case, you have your free list entries are scattered throughout your container at random addresses, so it's completely unpredictable, and it kind of makes sense. But like, if your access is predictable, it's not going to improve anything. Actually, it's going to make it slower just because now you have an extra instruction that you're having to do. So after doing these optimizations, I was pretty happy with the performance of modifications. And I decided to do some final benchmarking. So I decided to benchmark against the baseline format that we made at the start, and then against unordered map. In the unordered map version, I have 2 levels of nesting of unordered maps, just to replicate how my container is being used. It's because I'm creating like maps inside maps in my benchmark. And then our leaf values are going to be variants of int, double, string, and vector of int. And then I used heterogeneous lookup on the map to make it nice and fast. And I used the same hash format as my format is using, or the same hash function, sorry. And I also tried benchmarking against the flat hash map from Absale, just because I suspected it could be faster, but it ended up just being slower in every benchmark. So I think I might be missing a bit of a trick there. So I just stuck with unordered map for now. So in terms of performance, in read-only workflows, it looks like this. So our optimized format is doing about 10 million reads a second, which is pretty similar to an unordered map. Then our baseline format's an order of magnitude slower. And then as we increase the number of elements in the document, we only get slightly slower, and then our baseline is not even appearing now just because it's really slow. So at the, on the large number of elements, it's about 2 orders of magnitude faster, which is pretty nice. And then in the mixed operations workload, which is doing equal amounts of writes, reads, and structural modifications, it can do about 8 billion operations a second, or close to it. On this map, on this benchmark, I wanted to show the difference between the first fit and the best fit as well. Optimized FF is optimized with first fit, and then optimized BF is optimized with best fit. As you can see, they're pretty closely matched until you get to the large number of fields in the document. So at having about 1,000 fields in the document, it drops off quite a lot. I'm suspecting it's because it spends a long time walking through the free list, trying to find the best fit. So that's not so great. At those number of fields, it's better to use first fit, although as we've seen in the previous benchmarks, if you're using first fit, you're also wasting tons of space in your container. So it's got its trade-offs. In terms of limitations, as you can see, if you're using first fit, you've got a problem with fragmentation. And then if you're using best fit, you're actually getting slower as your document gets larger. So I was trying to figure out if I could find a middle ground between the first and the best fit. In practice, I've not got that far yet. It might involve having multiple free lists and having free lists for small items and medium size and large items. So and then the other thing as well is that because of the added metadata, we're actually having a bit of overhead per key and value in our arrays and maps. So if you're in a map, you've got an overhead of 4 bytes per key value pair, and if you're in an and if your element's in an array, it's got an overhead of 2 bytes. And the other thing as well is that our format that we've created has a lot of offsets in it. So it would be pretty easy to make this code go and read out of bounds if you wanted to. So currently I don't have any bounds checking at all in this. So if you were to read a serialized document out of a file and it wasn't a trusted file or something like that, you could easily just go and crash. And all the benchmarks in here are done with no bounds checking. So yeah. So yeah, conclusions are we've created a pretty fast schemaless serialization format which you can edit in place. It compares pretty favorably to using unordered map in memory. And I guess the unsurprising conclusion is that if you basically create an allocator and then create all your same in-memory data structures in a small buffer, you essentially are able to match your in-memory data structures. So yeah, it's kind of unsurprising, I guess. So yeah, I guess other conclusions to take from this is that if you're trying to improve performance, I'd recommend creating benchmarks that are highly parameterized. If you parameterize on a lot of things, you can spot how your code misbehaves in very specific kinds of scenarios. So for example, having a lot field in the document, or performing a lot of operations in a role, for example. And you should profile, and then try to make algorithmic and data structure improvements, and then yeah, explore all of the, all the fun stuff like vectorization, branchless code, and prefetching, and all this kind of stuff. So yeah, in future work, I'd like to explore how to compact the buffer in place. So I think I might be able to achieve higher performance in writes if I keep the fragmentation in the buffer under check. So I was looking into a few algorithms from garbage collectors in order to do that. I didn't make much progress yet on implementing them. Yeah, another thing I'd like to explore is to build a format which doesn't have any offsets in it. So essentially, a format where you would create an index in order to search it on demand. So I was quite inspired by the SIMD project, SIMD JSON project, where they essentially, on reading the JSON document for the first time, they essentially create an index in memory, and then you can use this to really quickly search it. And they use MD heavily to make it fast. So it seemed kind of cool. I wonder if the same concept could be applied to a binary serialization format as well. It could even just be a bit more friendly as well. You wouldn't need to worry about things like, I like a quote character appearing in a string or anything like this. And then the other thing I want to explore was compressing repeated keys and fragments of keys in order to save even more space. So yeah. A couple of resources I'd recommend a lot. The top one is a book that's available online. It's called Algorithms for Modern Hardware. It covers all this stuff in extreme detail. It's very useful. And then I started reading this book called the Garbage Collection Handbook, which is essentially how to implement various garbage collection algorithms. And you wouldn't think it would necessarily apply in C++, but it was actually extremely useful for getting an idea of what allocation algorithms are out there and so on. I've not even scratched the surface of this stuff in what I've done, so there's tons more to do there. And then I'd recommend this talk by Chandler Carruth from CppCon 2017 called Going Nowhere Faster, which I think was the first talk I watched that sort of explained how to how to benchmark and profile in a lot of detail. So that was very valuable. And then also, I hadn't attended it at the time of doing most of this work, but at the start of the conference, I attended Fedor Pikes' class on performance and efficiency in C++, and it was exceptionally good. So I'd really recommend that. I realized, walking out of there, I thought, yeah, I'm not really qualified to give this talk now. I don't know enough, so yeah, I'd highly recommend that one. And yeah, I think that's it. So So thanks. Yeah, anyone got any questions?
Hey, thanks. It was a really interesting talk. One thing I'm curious about, I was actually a little bit surprised that you only have 4 bytes of overhead for everything in the map. So I was wondering, like with only like 16-bit hashes, like do you have any idea how bad like collisions are in practice? And then the other thing I was going to say is that I guess the total buffer length is limited to 64K.
Indeed, yes. So every offset in the buffer is encoded in a 16-bit integer. So it's only good for documents that are less than 64 kilobytes. If you wanted to extend it to more, you would pay for like larger offsets, and then you'd have like more overhead. So, yeah.
Right.
Yeah, and then your other question was about the hash collisions. Yeah, no, I didn't measure it, so I don't know. In the worst case, you have to walk through a few hashes, and since they all appear in the same order as they appear in the buffer, you could just like walk through all the hashes that are conflicting and check if the actual strings match. Right. So yeah, I'm not sure. That's a good question. Yeah, I should try and measure that.
Okay. Yeah. Well, one thing that I was going to say, so one thing that's interesting with only having 4 bytes per key value pair, like I had done some work not too dissimilar from this in the past, and at really small, like not necessarily small buffer sizes, but at small numbers of keys, it makes your offset storage really small, and especially because you're using hashes here, like unless you have a collision, you don't actually have to go look at the packet data. Mm-hmm. And so what you can find is that at small numbers of fields, you can get really, really fast performance because everything stays entirely inside of the offset storage until it has to actually go get the data to return it to the user. Oh, yeah. So it's like in my testing, like you can, in my particular format, I could have up to 8 keys be on a single cache line. And so like you would have essentially identical performance for like the first 8 keys, and then it would start to like significantly drop off.
I see, yeah. Yeah, it makes sense. Is this when your keys are particularly small and you can fit them into a small amount of
No, so the idea here is that if you can make the entire binary search algorithm confine itself to just the offset storage because you're working with hashes or something like that, you don't have to actually go look at the key data until you've already found your match, essentially.
Yeah, yeah, it makes sense.
So I was just going to suggest that's another interesting benchmark case.
Yeah, that's cool. Yeah, thanks.
Cool.
Cheers.
Hi, it was a great talk, thanks. I was wondering, you've added actually the list of offset and the list of hashes because you are interested in searching and adding.
Yeah.
But what if you're only interested of serializing and deserializing as fast as possible? Do you still recommend to have those lists, or just the key tag is just enough?
No, I think if all you need to do is just write out keys and values as fast as possible, I would just use a tagged format and none of this stuff. So if you're just going to append a bunch of keys and values into the buffer, it's going to be as fast as it can be. So, yeah.
Hello, thanks for the talk. I'm interested in your benchmark setup when you mentioned that you compile with -02.
Yes.
I'm wondering why.
I'll have to go back really far for that. To be honest, each time I try 03, it doesn't make things much faster. So I just stuck with 02, and sometimes 03 has actually made things a little bit slower. So yeah, it would be interesting to try with 03 as well, though. So I should probably do that.
Do you run in prod with -02 as well? Or
I'm sorry?
Do you run in prod with -02 as well?
In prod world 2, yeah.
Thanks.
Sure.
Thanks, that's a good talk. Question mostly related to like append on the question, which was the last question here. So if we only look for a search and not go into modifications, do we have benchmarks, or did you try benchmarks on how the updates work in terms of only having append-only updates to the map, adding elements and not really kind of changing anything, so we don't need the pre-list or pre-list?
No, I haven't. But yeah, I suspect it could be quite a bit faster. Yeah. I think if what you want to do is just if you have a message and you want to write it out, then the fastest will just be append only and just like write out all of your data. So yeah, if you can avoid having all the other all the other like machinery and stuff to make the searches faster and to do the free list management. It'll just make things faster. Yeah. So.
Thank you.
No worries.
I was just wondering, you said like, for the best fit, you have like not so good performance. And you said something like this, but just for clarification, you have just one free pointer list basically, where you point to the free space.
Yeah.
And your idea is basically to upgrade that to have multiple free space pointers to point to basically equally or kind of equally sized spaces. That's the next step you want to approach, right?
Yeah,
to
exactly.
Make the best fit faster.
Yes. So basically keep, say, 3 or 4 free list pointers, and then you would have a free list pointer of, say, like space that's smaller than 16 bytes, and then space that's smaller than 32, and then smaller than 64, and so on.
So why are you not using the offset? So you have like basically a hash list. You have like the offset list, so you can also have that parallel to that and use the offsets as like the size difference.
Well, my problem is my offsets don't actually tell me how large my values are, just because those offsets don't all need to point to contiguously allocated values. I could be pointing here, 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 right? And I would say, you know, like offsets of like 6, like 200 and 1,000 or something. It doesn't tell me that my,
and
like...
Is it also including the conflicts? So that makes probably the problem, right?
No, conflicts don't really play a part in this. Like in what way would conflicts impact this? I mean, if you have a hash conflict, it's only in the array of hashes. So it doesn't really affect like where in the value, I mean like where in the buffer your value is going to be. So it shouldn't play any part, yeah.
Thank you.
Okay.
Before implementing all the allocation logic, have you tried using a caching or a re-allocator to see what they will do? Because they're usually very good at handling these kind of situations.
Yeah, I'd say an arena allocator, if I remember correctly, is pretty similar to a bump pointer allocator. So it's roughly the same as the first one I kind of showed. But yeah, I didn't benchmark that one much. And one thing I want to explore is if I implement compaction, could I combine that with a bump pointer allocator and then have extremely fast allocation and then just periodically like pay for a compaction. So yeah, I'd like to explore that for sure, yeah.
Thank you.
No worries.
Hello,
Hi.
I have 2 questions. First one is what are your consideration to choose the schemaless of serialization? And the second one, have you benchmarked against other serialization software?
Yeah. So the first question, like what made me choose schemaless? I guess the sort of motivation for this whole project was that in our code base, we have a number of serialization formats that are basically specifically tuned for certain workloads. So there's some that are just having like a sort of, you know, like just a single map and you can put in a bunch of entries. And then there are ones that basically provide you a sort of like array of maps, and then there's ones that are just sort of like more like a schema-based ones. And I was just kind of thinking to myself, can I create a thing that's, you know, essentially as flexible as all of them and then just replace all of them? Which I guess is the classic kind of thing, you know, as a software engineer, you always think, you know. Yeah, and then your second question was, have I benchmarked against another serialization format, which if I can scroll back far enough to the benchmarks where I compare against serializing, you know, every operation or every 4 operations or every 6 operations, which is going to take me ages. I wonder if it's faster on this. 1 sec. Yeah, much faster. Brilliant. So fast searches. Yeah, so here's the one where I compare against serializing every so many number of operations. And in this case, I've picked a popular schemaless format to do the serialization. I don't want to name it just because it feels a bit unfair. It's not exactly, it's not what it was made for. So I don't want to sound like I'm comparing myself against them and calling them like slow or something. So yeah, thanks. All right, cool. In that case, yeah. Thanks for coming to the talk. If anyone has any more questions, you can just catch me outside as well. Thank you.